So here are a few of the main items that we're going to cover in chapter 3. I'll start with the second and end with the first. There are three quantities of physical interest that we look at. One is the speed, one is the velocity, one is acceleration. Those are three main quantities that we've already talked about or we've began to discuss. We'll talk about them more here. And then we will talk about velocity vectors or the use of describing velocity as vectors and how we add vectors to determine the net or the resultant velocity when more than one velocity are being added together. Free fall is another topic that refers to objects that are falling freely under gravity. And we will learn that they have a fixed rate of acceleration that is the same for all objects. As we showed in last chapter 2 slides from Galileo's experiment, whether it's a heavy object or a light object, all objects fall under gravity at the same rate, and therefore they would reach the ground at the same time. So we'll talk a little bit about that and its relation to acceleration, and then we'll actually begin, and hopefully we will see other examples that what we call motion or velocity is relative to where the observer is when that velocity occurs. And we'll give you an example in the next slide. Stay tuned for that. All right, on this slide, what we're going to talk a little bit about is what's called relative motion. So one way to think about this is that the motion that you have, say, walking on the Earth, or the speed that you have walking on the Earth, depends on the location and the speed of the observer making the measurement of your speed or velocity. So as the picture shows here, you may be walking on the road relative to the Earth, and you may be walking at 4 miles per hour. But the Earth is moving around the sun, and its velocity in the orbit is thousands of miles per hour. And depending on which way you walk, you may add that 4 miles per hour to the motion of the Earth as viewed from the sun. So if the observer is measuring your motion from, let's say, the center or the surface of the sun, then he will see a different velocity for you than, say, the observer at rest on the Earth watching you walk by. That observer sees only 4 miles per hour. The observer at the center of the sun or near the sun will see you moving at the speed of the Earth plus the velocity, your 4 miles per hour. And that will usually be very, very small compared to the speed of the Earth. So your motion relative to the sun is different from your motion relative to an observer measuring you move on the Earth. That's one way of looking at this. Another way that I like to point this out is that imagine a car traveling along the freeway at 60 miles per hour, and there is a fly in the back of the car that flies to the front of the car at 5 miles per hour. Now, for the observer in the car, that fly is moving at 5 miles per hour. But for an observer on the ground, he sees the car moving at 60, plus he sees the fly moving within the car at 5 miles an hour, or that's not what he sees, but that's what's happening. So what he sees is 60 plus 5, or 65 miles per hour. And that is called addition of velocities. We'll see that a little bit further, but that's the whole idea of relative motion. In this slide, we are going to define what we mean by speed in a precise manner. Most of you are probably familiar with this from your speedometer and from watching sports events or other things such as that. So basically, a speed is defined as the distance covered by an object divided by the time in which that distance was covered. So if for example, a runner runs the 100-meter dash in 6 seconds, for example, then he is assuming he was had the same speed at the beginning, middle, and end. Then his speed would be 100 meters divided by 5 seconds, which in that case would be 20 meters per second. So that would be a way to characterize the speed. Another example, as you see here, is a girl runs 4 meters in 2 seconds. Her speed is 4 divided by 2, or 2 meters per second. In the next two slides, we distinguish between the types of speed. One is average and one is instantaneous. I think these are mostly intuitive to all of you, but just to mention briefly, the average speed is the total distance covered divided by the total time that an object moves, and it does not take into account or indicate any variations about that average. So, for example, in the example shown here, when a driver drives a distance of 200 kilometers in 2 hours, then they will have an average speed of 200 kilometers per hour. They may have spent part of that time at 90 kilometers per hour and part of that time at 110, but we only are measuring what the average is in this scenario. In the case of the following slide, which I will just mention briefly here, but we also have instantaneous speed, and that is what shows on your odometer, your speedometer, which indicates instantaneously how fast you are going. So those are pretty intuitive slides, and we will resume on slide number 7. Now, in this slide, we're going to talk about another property of moving objects, which is called acceleration. This was first formulated by Galileo by studying the speed of balls rolling down an inclined plane. And he was able to do measurements to determine how rapidly the speed changed as it went down the slope. And in particular, he could measure what was the change in velocity or speed of the particle after 1 second, after 2 seconds, after 3 seconds. And what he found was that the acceleration was the same regardless of what period of time that we looked at the ball, either in the first second of its motion, the second, or the third. So we come up with this concrete definition of acceleration as a change in velocity divided by the time over between which that final and initial velocity occurred. And so the units of that are going to be in units of meters per second, because if the change in velocity is in meters per second, and we divide that by the time, then we get meters per second per second. We abbreviate that by calling that meter squared. Another form of acceleration is that which is caused by an object moving in a turning or a circular path. So in this particular example, you see the car moving around a circular track at constant speed. That is to say, it is a fixed number of miles per hour, but the direction of the car is changing. And since the velocity is a vector quantity, namely it has a magnitude which is 50 miles per hour, for example. It also has a direction, but that direction is changing as the car moves in a circle, and therefore it has acceleration. Now, you can feel this as the driver in the car because, as you know, when you go around a curve, a turn at high speed, particularly if it's not a bank turn, then you feel your body being drawn to the outside or the side of the car, um, opposite the direction in which you're turning. So you feel acceleration, and that's true with linear acceleration as well. If you're in a jet airplane and you accelerate on the runway, you feel your body being pressed back against the seat. In this case, we have circular acceleration, and you feel your body not being forced backwards, but to the side of the car, opposite the direction of the turn. So it feels stronger as the speed increases or the radius gets smaller. And we have a mathematical way to calculate that, which depends on speed and radius, which we'll talk about in a little bit. This slide gives a concrete example of a calculation of acceleration. It states an example that we suppose that at one moment in time, the car's speed is 40 kilometers per hour, and at 5 seconds later, the car's speed is 45 kilometers per hour. So, based on our definition, we can calculate the car's acceleration. Uh, the change in speed is 5 kilometers per hour, which occurs over 5 seconds of time. Therefore, the acceleration is 5 kilometers per hour per second. On the next two slides, including this one, I want you to answer these questions. I think after we've talked, we've discussed the material in front of this, you will be able to answer this, and we will resume on a slide discussing acceleration and inclined planes immediately after these two questions. Now, good afternoon. This slide illustrates Galileo's experiments with objects rolling down an inclined plane. And as you can see, he did the experiments for various angles of inclination of the planes. And of course, the most important result, as you can see here, is that the steeper the angle of the plane, the more rapid was the acceleration that he observed. So he found that as the angle got steeper, the acceleration also got steeper. And the ball begins to change its velocity much more rapidly with time or per unit time as the angle increase. Obviously, there's a maximum angle, which in this case is 90 degrees, and that is when the ball is said to be in free fall, and that is when the acceleration will be a maximum. And in that scenario, and for all experiments done on Earth, that acceleration is approximately 9.8 meters per second per second. Sometimes we round that and call it 10 meters per second per second. On the next slide, we'll talk a little bit more. Now, this slide shows that when the angle of the plane is at 90 degrees, we say that the object is in free fall. It's the same as dropping it off the edge of a cliff, as you will see in the next slide. And under these conditions, and if there is no air resistance to the falling object, then all objects, regardless of their weight, will fall at the same rate of 9.8 meters per second per second. And this will be true regardless of what their mass is.